morning. It's a pleasure to be here today, and I will be presenting of mice, men, and mosquitoes, vector-borne infections in a changing climate. And I have no relevant financial relationships to disclose. Climate change is causing shifts in natural systems. The range, life cycle, growing pattern, and disease dynamics of many living organisms are being affected by the changing climate conditions. And human health is inextricably linked to the health of animals, plants, and ecosystems. The term One Health, I think, accurately encapsulates this inherent interrelatedness. Changing environmental conditions, such as temperature and precipitation pattern changes, are affecting the range and the life cycles of vectors and hosts of some infectious diseases. And these changes ultimately affect the health of people. Determining the role of climate in vector-borne illness is very complex because of multiple confounding variables. The disease incidence of these infections is impacted by human activities such as land development, travel, time spent outdoors, air conditioning, self-protection. It's much easier to identify a climate signal in changes in wildlife diseases. For example, an increased intensity and range of bird malaria has been easier to correlate with changes in the temperature than changes in human diseases. And this image here is an image of animal parasite interactions where experiments have linked change in disease risk with climate change. But we do know that changes in climate influence the habitat suitability and the reproductive rate for hosts, vectors, and microorganisms of some infectious diseases. So today I'm going to focus on just four, and these are Lyme disease, West Nile virus, dengue fever, and chikungunya. And these images, the purple and yellow is of the West Nile virus, and the green and yellow is a stain of the Borrelia burgdorferi bacteria that causes Lyme disease. So I'm going to start by talking about Lyme disease. Lyme is caused by the spirochete bacteria, Borrelia burgdorferi, and it's transmitted by the Axodes scapularis, or black-legged tick, in the northeast, north central, and mid-Atlantic regions of the U.S. In the Pacific coast, it's transmitted by the Axodes pacificus tick, and in Europe, it's actually transmitted by a different tick. And early signs and symptoms occur about 3 to 30 days after the tick bite, and they include fever, chills, fatigue, and the bullseye erythema migrans rash in about 70 to 80% of patients. Later signs and symptoms occur days to months after the tick bite, and these include multiple erythema migrans rashes, meningitis, Bell's palsy, carditis, and arthritis, primarily of the large joints like the knee. And Lyme disease affects about 300,000 people yearly, according to the CDC, although the majority of cases are not reported. And boys ages 5 to 9 are at the greatest risk. And below a certain temperature threshold, tick mortality outstrips their reproduction. So the populations die out, or they never become established. And that can be described as the basic reproductive number is less than 1. Northward expansion of the Axodes scapularis tick has been documented in North America, and this occurred after those areas became warmer. It did not occur before. This image depicts the change in the observed and projected basic reproductive number for the Axodes scapularis tick in North America. And from 1970 to the present, the reproductive number has increased in 4 studied Canadian regions and in Old Lyme, Connecticut. And further increases are projected with continued warming in these regions. And this increased reproduction may have co-driven the range expansion of the tick into more northern regions. And it also may have co-driven the increased disease risk in regions where the disease was already endemic, so particularly Lyme, Connecticut. And these would have occurred alongside other hypothesized factors that influence disease risk, such as reforestation of the Northeast United States and burgeoning deer populations. I would add, though, that Canada has not generally experienced a reforestation. In the Northeast, a lot of farms, areas that had been cleared for farming, now have more trees, and that's thought to have contributed to the expansion of Lyme disease in the Northeast United States. But Canada has not had that. They've had more of a net deforestation, so that wouldn't explain the increased incidence or the emergence of Lyme in those regions. And this slide depicts continued northward expansion of the Ahdoot scapularis tick into Canada due to rising global temperatures. The color scale represents the basic reproductive number for the tick, and with warming, the habitat suitable for Ahdoot scapularis expands northward. So image A is estimated from observations 1970 to 2000. B is projected for 2011 to 2040, and you see the region expands northward, and C is projected 2040 to 2070. And in the United States, Lyme disease increase has been predominantly in the north, in northern regions. Among the states where Lyme is most common, New Hampshire and Delaware have experienced the largest increases in reported cases, followed by Maine, Vermont, and Massachusetts. I'm going to change now to a discussion of West Nile virus. West Nile is the most prevalent flavivirus in the world, and it's carried primarily by Culex mosquitoes. It likely evolved in Africa, and it was first isolated in 1937 in Uganda. And between the 1950s and the 1980s, it spread to the Middle East, India, and Australia, and more frequent outbreaks started occurring in the 1990s. It was first detected in the US, in New York City in 1999, and then it spread rapidly throughout the continent. By 2004, it had spread across the contiguous United States, into Canada, and into Latin America. And human case rates are highly variable year to year. And West Nile is transmitted primarily, as I said, to humans by mosquitoes, the Culex mosquitoes. Additional routes have been documented, but they're a very small number of small proportion of cases, and they include, it can be transmitted through blood transfusions, organ transplants, through a lab setting, and it can be transmitted from a mother to a baby during pregnancy, delivery, or through lactation. And the majority of patients who get West Nile actually are asymptomatic, 70 to 80%. About 20% will get a febrile illness, fever, headache, body aches, joint pain, vomiting, diarrhea. And the fatigue and weakness can last for weeks or months, but it's almost always you have complete recovery. But severe symptoms are the neurologic sequelae, and they occur in about 1%. And patients who develop neurologic West Nile develop encephalitis or meningitis with headache, high fever, neck stiffness, can progress to coma, seizures, and paralysis, or death. And recovery may take weeks or months or may result in permanent impairment. And it's fatal in about 10% of people who develop neurologic infection. This slide describes the West Nile transmission cycle. And in nature, West Nile virus circulates between mosquitoes and birds. An infected mosquito bites a bird, the bird gets infected, and then the birds can develop high enough levels of viremia that when another mosquito bites the bird can transmit West Nile back to a mosquito. And that infected mosquito, within about a week, can then transmit the virus themselves. So that's the typical cycle. Humans and other mammals are considered dead-end hosts in that we don't generally develop a high enough level of viremia to transmit it back to a mosquito. So we can't transmit the virus to mosquitoes to complete another round of cycle, generally speaking. And elevated temperature has a positive effect on mosquito populations, on the rates of viral replication, and on West Nile virus disease transmission. And this image depicts the rate of virus replication for the West Nile virus, as well as two other viruses, as a function of temperature within two Culex host mosquitoes. And you can see an increased rate of replication as temperature rises. This is, I think, a very interesting study from 2006, which found that temperature has impacted the dispersal and amplification of West Nile virus in North America. And West Nile always dispersed into new areas during years with above normal temperature, meaning greater than the 30-year mean. and amplification the following year occurred during summers with above or normal temperature. And activity decreased during summers with cooler temperature, primarily in northern latitudes. Drought also may be associated with increased disease activity, and this is somewhat counterintuitive. But the 2012 outbreak in the southeast United States was one of the most severe on record, with over 5,600 cases, over 2,800 cases of neuroinvasive disease, and 286 deaths. And this occurred after a historic drought with precipitation levels lower than during the Dust Bowl time and with extremely high temperatures. This is an interesting image of global distribution of epidemics of vector-borne outbreaks between 2010 and 2012 that were associated with extreme weather events. The green is the West Nile outbreak in 2012 in the United States, which was associated with extreme drought and extreme high temperatures. The yellow is from the first known outbreak of dengue in East Africa, which was associated with a severe drought, high temperatures, and famine in 2011. The red is a Rift Valley fever outbreak that occurred in South Africa following a period of extreme heavy precipitation in 2011. And similarly in Australia, there was a Murray Valley encephalitis outbreak also following a period of extreme heavy precipitation in 2011. And this slide depicts the probability of the presence of the West Nile virus in mosquito vectors as projected for the years 2050 and 2080. And areas in red are those that indicate an increased probability of presence of the virus, which was considered more than 10% compared to today. And blue areas are those that indicated projected decreased presence of the virus. And northern latitude increases are related to an increased temperature, projected increased temperature in those regions. Whereas in the middle of the continent, the increased projected presence is due to projected decreased rainfall. So it's thought that the decreased rainfall in the middle of the continent will lead to increased West Nile virus in those regions, whereas in northern latitudes, increased temperatures are projected to increase West Nile virus in those areas. The blue that you see, which is projected decreased probability, is thought to be due to projections of increased rainfall in those parts of the continent. So again, it's this relationship that seems to exist between less rainfall, drought seems to precipitate West Nile virus, to lead to increased prevalence of West Nile virus. And I'm now going to switch to a discussion of dengue and chikungunya. So dengue likely originated in Africa or Asia. It's not certain at this time. And it's the most prevalent and rapidly spreading mosquito-borne viral disease in the world, with an estimated 400 million cases yearly. It's one of the leading causes of death and hospitalization in children in the tropics. And up to 50% of patients are asymptomatic. Symptoms include high fever, severe headache and eye pain, muscle and bone pain, rash, and they may be followed by hemorrhagic manifestations. Chikungunya was actually first described in 1952 in Africa, but it's thought that outbreaks of it centuries ago were actually confused with dengue, and that it's been occurring for hundreds of years. And the word chikungunya translates to walk bent over, which describes this appearance of people who contract the disease who have severe joint pain. The symptoms include acute fever, muscle and joint pain, and nonspecific rash. And as opposed to dengue, which has about 50% of cases are asymptomatic, only about 4% are asymptomatic. 20% have severe recurring joint pains a year after initial infections. And the case fatality ratio is about 1 in 1,000, primarily in newborns, elderly, and the debilitated. Now, whereas West Nile is carried primarily by Culex mosquitoes, the Aedes mosquitoes are primary vectors for both dengue and chikungunya. There's the Aedes aegypti, which is the classic vector, and the Aedes albopictus, the Asian tiger mosquito. And I thought an interesting little fact was that chikungunya acquired mutations in 2004, which would first enabled it to be transmitted by Aedes albopictus, or Asian tiger. And these mosquitoes have originally forest dwellers, but they've adapted very well to living in human communities, suburban and rural areas where humans are present. And understanding the impacts of climate on these infections is very complex, and at this point they're incompletely understood. But research does show that both minimum and maximum temperatures limit mosquito development and mosquito survival. Increasing temperature shortens the mosquito development time, although this differs because there's different strains of mosquitoes, some which do better in tropical and some that do better in temperate climates, so it's not consistent. But climate change can expand the vector range, extend the transmission season, shorten the mosquito life cycle, and reduce time to mosquito infectivity. The effects of precipitation on Aedes mosquito populations are not fully understood. This depicts the effect of temperature on the rate of Aedes albopictus immature development. And you can see pretty consistently that as temperature rises, the time it takes for their immature development shortens. So they have their rate of development increases with increasing temperature. So their life cycle shortens. They go through their stages faster. This slide depicts the estimated effects of weather variables, the minimum temperature, maximum temperature, precipitation, and the non-climate variable of access to piped water, and how it's impacted dengue incidence over the past 23 years in Mexico. And you can see there's a pretty direct relationship between minimum temperature and increased incidence of dengue. But there does seem to be a threshold maximum temperature at which dengue incidence decreases. So it just gets too hot for the mosquitoes, theoretically. That's probably not good for us either. And then the relationship with precipitation patterns is less clear. But there's also human factors and are very important. Access to piped water. When people have piped water, they have water containers. And those containers of water are where the mosquitoes like to breed and why they're doing well in human settlements. So I'm going to finish my presentation with this summary that the health of humans, animals, and ecosystems are inextricably linked. And vector-borne infections are central to the concept of One Health. But further understanding of these complex relationships is needed to enable our communities and health systems to effectively anticipate, prepare, and control these rising health threats. Thank you very much.